On to the lesson here. Nicely related. I'll be able to get to this one. So today's lesson is called Equations and Graphs. Of polynomial functions. In this unit, we'll just be graphing the x-intercepts. Remember to use end behavior. Today there will be graphing, which means I would like you to do this on graph paper, please. So if you do not have a piece of graph paper, Fox, I'm looking at you, if you could talk to your neighbor and gently say, "Man, please borrow a piece of paper today." For those that were not in my class last year, Fox, I'm going to borrow your paper if you don't mind. What I expect your graph to look like is this. You're going to take your paper, you're going to fold it not once, twice. Okay, so you're going to make your graph paper like this. You can do then 1, 2, 3, 4, 5, 6, 7, 8 graphs on one piece of paper. Okay, make sense? If you want to do more, I did 4 like this. If you want to do more, you can do 4. You can do more than that, but that's 8 graphs on one piece of paper. That has to get you all I get more. Okay, so if you're a perfectionist and you don't want to do that, you don't have to. That's just a good guideline for people to do. I would like you to get and have these and rulers and all that stuff. So if you don't have a ruler today, that's fine, but make sure you get one Boston by Monday, please, okay? So example 1, you guys should be able to know how to do this. I'm going to say graph. And that's it. Go ahead. I'm just going to go through what I tell all my classes to do. Need arrows on the graph, and you're submitting this on an assignment or a test. Okay. So you might as well practice now on your notes. Arrows on all 4 corners, and there'll be 6 when you get to calculus. You need an X or an X-axis on the side, and a Y and a Y-axis on that side. You're going to make sure that your graph fits on the paper. Okay, so I skipped a line, so I used every 2 boxes, or every 2 squares to represent 1. Okay, you can do it. Everyone as well, right there. Okay, I'm going to put my x-intercepts in here. From here, what are my x-intercepts going to be? Okay, so -2 is going to be here. +1 is going to be there. And +3 is going to be there. Okay, if I wanted to, I probably could get the y-intercept too. Do I have a neat graph? You guys don't want a neat graph. Want a neat graph? I want a neat graph. I'm going to put 6 in here too. No, I won't. Okay, what's the end behavior for this one, please? So I'm going to somebody else say it, please. Go ahead, Callum.
X goes to infinity, y goes to infinity.
Okay, good.
X goes to -3, y goes to -3.
Very good. Okay, so all that means is at the end of your graph, that's going to happen. That's all that means, right? Okay, so now we got to connect the dots. How am I getting from -2 to +1? Yes, just above, like here. Okay. How do I get from +1 to +3? Underneath that. And that's all there is to this, okay? Until I put the next trick in here. I'm going to call that example 1. Okay, that's what you need to get full marks on your graph on a test or an assignment. All right. Are we feeling okay on that so far before I continue? Yeah, go ahead.
So like, how do you know how steep to do the between dots?
See, the thing is, you don't until you get to calculus. Okay. What the only other point you could get is what Peter was doing. I think it was you, Peter, is your test points. So you could do test points in between to find the exact values, but that's potentially a lot of work, right? So right now, this is enough for what we're doing with it. Okay. When you get to calculus, you can find these instantly. Okay, here we go. Example 2. Now, please put hopefully example 1 wasn't too stressful. For example 2, please put a star and a heart beside the page. All right. Okay, now, what is more off with this one than the last one? Peter, go ahead.
It's squared on bracket x plus 3.
Yeah. Now, if you think back to 2 days ago, we talked about this, or maybe it was yesterday, I can't remember. Was it yesterday? I think it was yesterday we talked about this yesterday. Do you remember what the square thing was for a parabola like that? And Dexter, go ahead.
Bounce off.
It's going to bounce off. So this would be like if you think how a quadratic, and it was when the vertex would be right on the axis. Okay, so this is going to be what we call a double root. We're going to say a double. I'll make a little mini note here if you don't mind. A double root will bounce off the graph. Same bracket, not change signs. An odd root goes through the axis. Okay. So if something's cubed or to the 5th or to the 7th, it will switch signs from negative to positive. If it's squared to the 4th or to the 6th, it'll bounce off. So think about like when we did the graph of x cubed compared to x. Y equals x goes straight through. X cubed, there's a little bit of a ditch, right? X to the 5th, it looks basically the same with a little bit of a ditch. The same thing happens for each root. Okay. Now I'm going to show you what this looks like. I'll let you guys to try a few on your own hereafter. Okay. My roots here are going to be, I'm going to say a single root. X equals 1 and a double root at x equals -3. Are we okay on that logic there, okay? Okay, there's two roots or a double root of x equals negative 3. Let's show what this looks like using graph paper. By the way, if I go too quickly, someone please stop me. If not, I'm just going to pretend you guys all completely understanding me. Slower. A single root is just like a regular, like to the power of 1 is a single root. Right? A double root would be degree 2, triple root would be degree 3, and you know what I mean? Like, so, excuse me. Double root would have like something squared here. If this was x plus 3 cubed, that'd be a triple root. Right? Or x plus 3 to the 4th would be a, oh, it's after triple, quadruple? Quadruple root, yeah. Okay, so all that's going to happen for this one is, I use my ruler and all that stuff. Still right there? Yeah, you still pause right because x times x times x is still positive for this. Negative 1, negative 2, negative 3, 0, 1, 2, 3. So, let's look at x's negative 3. Oh, I should move that over. Maybe I will. See how well technology works for me today. Ah! Yes, see how well technology works for me today. Ah, perfect. Okay. Okay, so my roots here are at, we said, a single root at 1, which should be here, and negative 1, negative 2, negative 3. Okay, can someone remind me here for this? This is going to be a positive cubic function. Can someone explain to me first why this one's cubic? Why did I say this one's going to be cubic? Yeah, why is that? Power 3. If I multiply the leading term by x times x squared, it's going to be x cubed. Why is it going to be positive? Not a trick. Go ahead on this. You guys positive, right? Like 1x times 1x times 1x is going to be 1, so that's fine. What's the end behavior of a positive cubic function? Now go ahead.
Positive cubic function?
Yeah.
From quadrant 3 to quadrant 1.
Quadrant 3 to quadrant 1. So I'm going to go.
X.
Good. So that's what's going to happen. Now here's the issue, right? What it looks like it should happen is something like this, right? That's based on the roots, okay? But because this is a double root at x equals negative 3, it's just going to bounce off like this. Look. And do something like this. Okay? So instead of going through at negative 3, because it hits twice, it's like a parabola, it's going to bounce off. Yeah, go ahead.
In the little mini note, when it says an odd root goes through.
Yeah.
What do you mean then?
I'll show you in the next one. Okay, I'll do something tricky like that. Okay. So an odd root would look sort of a lot like this one, right? So instead of like, it would go through the axis like a regular root. So it looked like this, but instead of going sort of straight through like this, it might go, if there's a root, it might look something like this. That's the only difference. And you'll see that on the graphing calculator, right? Like, but well, it's just the idea of the logic if it's positive or negative that I'm more interested in for right now. Okay. Can I get everyone to close their eyes and put their heads on their desks for a second? Sorry, Brian, this is coming back to grade 9. Can you close your eyes, Colin, so you can't see? Who is thoroughly confused at the moment? Okay, who is somewhat confused at the moment? Who pretty much feels awesome right now? I don't know who didn't raise their hand. Oh goodness, you guys are being difficult. You know I only have 3 options. Okay, you can raise your heads now. Okay. I think overall people are sort of good on this. Okay, we'll do a few more with the doubles and the triples to see. But example 1, I'm hoping people were fine at, like the first part. Right, this one's a little bit more confusing with the second one. Okay. Here we go. Let's do one more. Oh, we got lost. Still. What else do I want to cover? I'm glad you asked. do it right now. Here we go. Triple root. Example 3 is so this one is a little bit more awesome than the last. Okay, first of all, you can do this. I'm going to help you though. You can do this. All right. First of all, what is the degree of this graph going to be? Degree 4, right? Because if you take a look, x, 2x cubed is going to be like cubit on the right, times another x, which will be degree 4. So this is going to be degree 4. Is this going to be a positive or a negative? This, yes. It's going to be negative. Okay, so this is going to be a negative even function. All right. What is the end behavior of a negative even function? Now, if you haven't raised your hand today, yet you've found a way to insult the teacher, this is the time to think about raising your hand at this moment. What is a negative even function? Oh, come on, you guys. Okay, it's all right. So even functions are supposed to be like parabolas, right? So how does a negative parabola look? Yeah, so down and down. Yeah, okay. So we're going to say here, as x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative. So please be brave and ask, because we're using these concepts every day, right? So stuff like this. All right, let's look for roots here now. What are my single roots going to be? What's my single root going to be? Yeah, go ahead. Yeah, so on a single root, is going to be x equals negative 2. Double roots, I say none. Triple roots. Okay, where's my triple root at? Brian, I'm going to pick on you. Where's my triple root at?
X equals 3. 3 over 2.
Right, because this would be equal to 0, right? So x equals 3 over 2. All right. Now, here's the time to be brave and ask a question before I graph this. You're okay? I just pulled that from the equation with nothing else. Please be brave and ask. Riley, go.
This might be a really dumb question.
I doubt it would be.
How do we know it's degree 4?
Degree 4. No, it is a stupid question. I'm glad you asked it. Because that's stupid. I'm going to say it's a wonderful question. Okay. So where I got that from was if you just think of if you're just multiplying the x.
Oh, yeah, okay.
Right? So it's the same as in the leading term. That's all you care about. So x and x and x and x. Right? Yeah, go ahead.
Do we know it's negative because there's a negative 3?
Yeah.
Yeah.
Yeah. So basically what I should probably be doing, and we'll see how I think about it tonight, but I should actually multiply x times 2x cubed. So it's going to be 8x cubed times x is 8x to the 4th, times negative 3 is negative 24x to the 4th. So that's what your leading term is negative 24x to the 4th. Yeah.
This may have been answered already, but I zoned out for a second.
No problem, you're on it.
So are all like odd exponents gonna be piercing?
Yes.
Alright.
Yes. Yeah. And it's going to be, that's what sort of thing. Yeah, I said it over here. That's what I'm saying. Okay. So yeah, it's but yeah, so it'll go through. It won't go through it nicely like this. So when you graph, it'll sort of be. It'll look like the x cubed graph. Sort of change. So here we go. Let's graph this. Sorry, any more before I graph this? Yeah, go ahead.
So just the negative 3 at the front doesn't involve any of the roots. It's just the
Exactly. It's just the coefficient, the a coefficient at the start, right? It doesn't affect the roots, or the roots or the anything else. Anything else before we start to graph? Let's graph this. Okay. I'm so glad I have my smartphone back. I have to do this on paper? Oh, did I say it? No, I'm just joking. You guys, but I recommend when you're doing your homework, like, do it on hand, but if you need to confirm on Desmos or another program like that, I do happen to like Desmos, that's why I say it, like, there are other graphing calculator programs out there, right, but that one's free and it's excellent, so you might as well use it. 0, 1, 2, 3. I'm going to use every other square here because I have a 1/2. Okay, so there's x and there's y. I'm going to put my roots in here. I have a root at -2. And I have a root at 3/2, which is right here. Okay, let's talk about end behavior. We're not bugged yet today. End behavior for this is going to be what? How's the what's going to happen here on the left and on the right?
So, like, when your x is positive p, your y is negative p, so it's going to go down.
Yeah, so just all that means is from here to the right, we're just going to go downwards like that. Okay.
And when your x is negative p, your y is also negative p.
So it's just going down like that. Good. Are we okay with what's happening, the logic there? Okay, good. All right, on the left-hand side, we have a single root of x equals -2. So that just means do this. Nothing's going to happen. It's going to go upwards like this, something like that. Okay. The fun is going to happen on the other side. A triple root is going to look like x cubed. It's going to go through it, but it's going to be a little bit curved. Now, I'm not going to be super picky about this. Okay. If you want to make your graph look perfect, you can do it. But we're using our hands, not our graphing calculators. Okay. It's going to look basically like. Oops, let's get the circle back. Like x cubed. Remember, for x cubed, there's a little hitch to it, so the same thing's going to happen for that. Okay, now if your graph isn't perfect, that's okay. It is. How do I explain that? Well, if we do a table, it is hitting it 3 times. Think about just like that. Let's go back to that parabola. Okay, if you do a parabola, right? Oh goodness. If you do a parabola, all right, it's just going to bounce off like this, right? They're both going to head down and then hit once. So even though there are 2 roots coming from 2 directions, it's going to hit once. All right, so let's go to cube now, okay? If you're doing something cubed, all right, 2 cubed is 8, right? Yes? 1 cubed is 1. 0 cubed is 0. -1 cubed is -1. -2 cubed is -8. So it's still a number cubed that equals that y value. That's all we're saying. So basically what I'm saying is, whatever this number is, 3/2, 3/2 cubed is equal to 0. So that's going to make, going back to my chart here, right? Because all I need is this number to be 0, right? So if it's 3/2, it's going to be 0, right? If x is 3/2, that's 0. Not helping. It's just, I don't think the best way to explain it. Let me think here for a sec, the best way to explain it. I mean, it's just, you're just like, I don't know. Let me draw this first, I'll say.
How many times is that again?
It's hitting it 3 times.
That one?
It's, let me rephrase. It's going through it once, but you're taking a number and cubing it. Like it's only going through the line once, right? But because it's a cube that's doing it, it's not going through straight. It's going to go through as a curve. That's all I'm saying. Okay, so even this line here is still only one line. It's only technically going through it once, but because it's a triple root, it doesn't go directly to the equals as a curve. So, okay. Like it still only goes through once, right? On the negative side of 3/2, it's going to be above 0. On the positive side of 3/2, it's going to be a negative number, right? It's still the same thing. But if that was only times 3/2, the graph would look, the only difference between those two graphs, it would look like that. That's the only difference between them, right? So it's just a little bit of a wiggle to it. That's the only thing.
So for that, 3 times.
This is still only going through it once, so that's a cubic graph, right? That's still only hitting it once as well, right? If there's only one x-intercept to that, right? For, like, think about vertex, the vertex is on the axis, so we're staying in one axis or so. All right, but you'd write that as x minus 2 squared, that rate double root. Right, like if you were to graph this equation, right, this would be something like this. Right, so that's a double root, it just nicks, it doesn't actually go through. Okay,
I thought something degree 4 was supposed to look like a W.
good question, let me try and feel this. Degree, if you do the plane degree 4, it looks like you do still, but it's shrunk up. If it's like x4 minus x cubed plus x squared and all sorts of weird stuff, then it looks like a W.
And that would be a W.
Well, it does in a way. Okay, it's just plain. You want to know what it really looks like? Well, I'll go to the real graph. It's not quite like a W, but that's how it's going to look. When I'll show you on the, I'm going to pause. You guys are in a fighting mood today. Oh my goodness. 20,